So welcome to the first real robotic lecture that we'll have about the attractor dynamics approach to its really vehicle motion planning. Behavior generation is a bit general. And I'll use now concretely the ideas we had in last week's Dynamical Systems tutorial around this one model example. That's the example we'll be using. You will see later that it is quite a generic example. It actually covers a whole range of animal motion, which is really what's sometimes called navigation, how you move as an organism along surfaces. Actually, birds and fish do that in 3D as well, but we'll only talk about surfaces. So the path planning, not talking about the legged, moving the legs to do locomotion, but the path that you do, how you displace yourself in a plane. I'll show you how humans do that in this lecture and talk about animal locomotion in, I think, 2 lectures down. And I'll talk about how to use this to make robots move in the plane. So let's just begin in with a survey of the kind of ideas that I'll discuss. I'll first talk about behavioral variables. There will be only one here, but it will generalize through that concept. I'll show you that in a later lecture. And the notion will be that we will generate time courses of these behavioral variables from dynamical systems, and in particular from the attractors, or structured by the attractors of dynamical systems. So the system actually follows these attractors. And then bifurcations will be the way how this becomes flexible. So how the system does more than just control, for instance, how it can make decisions, be flexible. That's what happens. So the example, the behavioral variable we'll be using is the variable called heading direction. And that is quite a specific variable, but it's actually also a really biologically very relevant variable. That's a variable that you'll see that plays a big role in understanding how animals navigate, for instance, how they orient in the plane, how they orient to targets. But for now, I'll just define it technically. So we have a robot. This blue circle is a symbol of a robot. So we'll always treat these robots as systems that can turn on the spot. So you can think there's a wheel here on the left and a wheel on the right. It could turn on the spot and it's passively stabilized. So we're not dealing with this whole issue of how cars, like 2-axle vehicles, have much more complicated kinematics. And that's a whole different topic. So this is a trivialized version. A lot of robots that are used for autonomous robotics are actually like that. They can turn on the spot. You will see later that plays a role. And so their motion can be characterized really by how they are oriented, because instantaneously they will tend to move along their forward direction. So if there's a wheelie on the right and wheelie on the left, then they will be moving forward. Of course, they could turn, and that turn would mean that when the nose is, the forward is, would be rotating on the spot, right? But this nose is characterized by the anatomy, if you want, of the robot. These red things are sensors, and I will not really talk about these sensors until next lecture. It's just to have the same image here, right? And so the heading direction describes how the robot is oriented at any moment in time, and it will instantaneously, at that very moment, be moving in that direction. Although the heading direction can change, but if the heading direction changes a little bit slower then the robot moves, then it will move, the path it will make will have as a tangent that current heading direction, right? Except, if the speed is 0, then it will rotate on the spot again. It is defined relative to a fixed world axis. That's important and somewhat confusing. It would be easy for you to think of this if you know anything about navigation. If you're on a ship or a boat, then you are talking about the heading of the boat. And you do that actually relative to a measured world axis, which is typically given by the compass, like given relative to north. You would say, I'm steering 30 degrees from north, due north. And that's how you can control your ship's motion. The other thing that you can vary is the speed through the water, the forward velocity, and we'll get to that. And so we're conceptually using the same sort of thing, even though we don't need a compass. And you will later see that it doesn't really matter what this world axis is. We could have a compass that's totally off, and it wouldn't really matter as long as we have sensor information about where we want to go. I'll come back to that. It's a little bit confusing initially. It's not really based on the vehicle. It's in terms of orientation, it's relative to a world frame. It is, the world frame is sort of translationally centered in the vehicle. You know, so that's really nice. You have some world reference with respect to orientation, not with respect to translation. You don't need to know where you are, but you need to know where north is, let's say. Good. So that's a good variable because it tells you're able to express constraints for your motion in terms of values of that variable. That's one of the criteria for what are good variables. I'll give you a excursion, perhaps I'm not entirely sure, into a robotics. I think next week I will give you a little excursion into a system where we do the same, but we take the derivative of this variable as a behavior variable. And then it's more complex to express these constraints. So here it's, for instance, if you want to move to a particular target, you can express that as a desired heading angle. You could say the angle relative to that world axis under which this target appears, that is the angle I want to have. So I want my current heading to be equal this heading. And if that was the case, then I would be going straight for that target. And that's actually what you do in navigation on a ship. You determine the angle relative to north that you have to steer to head for your target point, right? But if you want to ram another ship, all you have to do is to measure the angle that ship under which you view that ship relative to your compass, and then if you steer that direction, you will be colliding with that ship. The obstacle avoidance can be expressed similarly. In obstacle avoidance, you have a certain angle called psi ops here, under which you see the obstacle relative to that world axis. In obstacle avoidance, typically you might think of the obstacle being a whole range of angles because the obstacle might be extended in angle, and you may want to avoid any angle within that direction. And so it's like the closest you could be right here on the side of that, and on the other side. And we'll later think about how much of a safety margin you might need to include in your steering. And there will be issues like you don't want to avoid an obstacle when it's very far, so distance dependent will come in. But in terms of the information, that is what obstacle avoidance imposes as a constraint, the heading direction expresses that well. So these are values or ranges of values that determine the behavior. But these are criteria that we use to select or to characterize behavior variables, and that's something we can ask about nervous systems, animals, if they fulfill that. So what I described is that you can express or describe the desired behaviors for a robot, or maybe the observed behaviors for a animal, in terms of these variables as values or sets of values, or also as trajectories, so time courses of such variables. The other aspect, of course, is that these variables are sufficient to then generate behavior. I wrote down here enactable, I'm not even sure that's a word, but that you can, so there's an engineering term called controllable, which has a much more specific technical meaning. This is not quite the same, although very typically you would also ask for that. So can you actually bring about behavior that is then realizing particular values of this this variable? And in this robot, as I was hinting, we would be possible, it would be easy to do that because we would typically assume that there are two active motors, for instance, here on the left, on the right, two wheels that you can turn freely. And so by giving these two wheels a joint velocity that moves the vehicle forward and creates constant heading, and by giving them a slightly different speed, we can make the robot move forward and turn. Generally, the mean of the two speeds I give to these two wheels would be the forward velocity, and the difference correctly scaled with the size of the robot, the size of the wheel, tells you the turning rate. So you're able to create constant values for this variable heading, but you're also able to change it. And in fact, you're able to impose a certain rate of change, a certain angular velocity onto the heading, and then that will create out a trajectory. And already talked about these ranges here, and appropriate level of invariance. Yeah, that's a more subtle issue. So what we essentially need is that the constraints that we have for these variables don't depend on the current value of these variables. So for instance, if you have this kind of situation, this would be where the target is seen under this angle. So this is, let's say, 20 degrees from that fixed axis. And currently the robot is heading in this direction. But if the robot was oriented differently at this moment, right? And maybe it was initially oriented in this direction, maybe it rotates on the spot, then the behavioral requirement doesn't change because it's expressed in that world representation. It's a constant and invariant under rotation on the spot. And the maybe more intuitive thing that many of you might think of initially is that we might want to determine the heading relative to the robot coordinate system. Like this is where the robot is looking forward, right? And this angle here would be the bearing from the robot's point of view of this target, you know, which is called in German Peilung, how we would be looking at this target. Now that is actually not a good variable, because now if you rotate in the spot, that value changes. So you can't actually say what the behavior requirement is. It depends on that value. In fact, the only thing that you could do with that is to say, I want that angle to be 0, then I would be heading right for the target. And you see that will be a problem if you do that for an obstacle, because an obstacle would mean, well, I just don't want it to be 0, but no, which angle do you want it to be? That's not clear. So we're talking about the invariance, that is the behavior variable, and the constraints are supposed to be independent of each other. One is a value of that, but that value does not depend on the current value of the behavior variable. And you will see when we do this dynamically, that's a critical property. Next week, I will be really focusing on that. So then the next step is that we create our behavior by creating time courses of the behavioral variables. And our particular idea is to use dynamical systems thinking, that is to generate the time course from a dynamical system, but just not any. We'll do it from a dynamical system that has as a special solution of the dynamical system, an attractor solution, a stable solution, and that will essentially give us stability properties now in planning, because we're not really yet talking about how the robot would then actually control this in the sense of physically, activating the wheels to do the right thing. In all the examples I've been talking about, we assume that that problem is somehow trivially solved. That is, you have servo motors that can approximate any desired velocity for the wheel. So if the robot is, for instance, on a carpet, has more resistance, or is on a very hardboard floor, let's say, this is a different system that takes care of making sure that the wheel turning corresponds to what you desire. So the stability is not the stability that is required for the control system. It is the stability of the planning system, but that plays a similar role. And you'll see that it plays the role that the system will be able to deal with time varying sensory information about targets. For instance, if the target were to shift as you're moving, this stability would automatically care of the robot compensating for that shift and catching up with the target, tracking the target. Or if there was some other influence like obstacle avoidance, and then when that pushes the system away from the target, and when that obstacle avoidance goes away, the system will be able to recover the desired solution. Well, it's a general idea that dynamical systems are used to integrate multiple constraints, that you have multiple virtual forces in a sense in this dynamical system, the rate of change, and then these forces can be combined in the dynamical system. So this is, for instance, also the key idea of the movement primitives approach that I will be talking about in the second part of the course. So the way we set up this dynamical system is that we add different contributions to the right-hand side, the rate of change of the dynamical system, that express the different constraints. And here's the simplest constraint, the constraint to move to a target. This will be the dynamical system. It's now of heading direction, right? So here phi is the current heading. This is the rate of change of heading. The rate of change of heading is simply the turning rate of the robot, right? It's always the planned turning right. It's a different thing than to actually physically achieve it. But for now, I'll always assume that it can be achieved. So that's a function, and therefore this makes this a dynamical system. And what we'll do is we'll erect an attractor at the heading direction that corresponds to that desired heading direction of the target. And so the zero crossing with negative slope makes it an attractor. Remember that we arrange for that zero crossing to be here at that right location. And the obstacle avoidance constraint can be very analogously be imposed by erecting a repeller, so a fixed point with a positive slope that repels in the direction in which the obstacle lies. And what we'll have to do is we have to make sure that the region over which you're repelled, reflects here the width of the obstacle. I'll come to that in a moment. You might be a bit surprised why we use a fixed point here. Why would we not say, well, if I'm heading, if I'm heading close to the direction that is forbidden, I'm going to turn very rapidly, so I'm not making the turning rate 0 there. But you see, this is essentially a decision if I go around the obstacle on the right or on the left, and this is sort of the decision point, right? And if I were to make this dynamical system now a non-continuous dynamical system, so let's say you have a very negative rate here, and then you jump to a very positive rate here, that might be, maybe considered maybe a more rational behavior. Then you would have a discontinuity, which would create mathematical problems. And there's some not so important problems of just things being well defined and so on. But the pragmatic problem is that will create situations in which there will be some forms of instability. That is, if you have this behavior and you're running through that direction, you're turning through that direction, then there will be radical changes that might not even be controllable, and that can actually lead to oscillatory behavior, where you will be pushed in a certain direction, but as you cross into that regime, then suddenly you're pushed in the opposite direction. And why would you even go through this region? This is the region try to avoid. Well, obstacle avoidance will be just one contribution to the dynamics. You will have, for instance, also attraction, and if you're to the target, and if the obstacle is far enough, it will be a small contribution, and the target contribution might dominate, and that might push you to cross this boundary where there's a jump in the heading direction. So we need to be clean, have a dynamical system that has really a continuous right-hand side, the forcing function being continuous, to guarantee that we get the properties of the dynamical system: smooth, continuous, differentiable time courses. So that's where we end up going through 0, there where we make a decision. So in practice, when we write this down, we write things that we call forcelets, that is, contributions to the dynamical system that are parameterized by where the 0 crossing is. That will be a specified value. For an attractor, it's the value, where this is a negative slope. For a repeller, it's the opposite. The strength is essentially the slope of the dynamics, because if you the strength relative to other terms. So if you have multiple terms, and we'll look at that in a moment, these multiple terms would be combining here in a way that depends on how steep the slope of this function is. The steeper, the stronger. This means when you're deviating a little bit of it, how strong is the restoring force? How strongly are you pushed back, or in the case of a repeller, pushed away? And then there is the range. So forcelet, with the notion that typically there will be a limited range over which these contributions contribute. For a target acquisition is sort of an unusual case, because there we really want to reach the target from just any initial condition. So we would have the complete range. In the case of an angle, right, it's a limited space, a periodic space, so we'd have a complete range. A periodic space is special, it's periodic. That means the dynamical system must wrap around in the back, and therefore we're using sine and cosine functions to actually write down these equations. If we were to have variables that are not periodic, we would use these normal forms that I discussed last week to get the attractors, and later you see the repellers right. But other cases like the obstacles will actually use ranges that are not the whole circle, because for instance, an obstacle, you don't really want to be influenced by an obstacle if you're already heading away from it, right? So there's a limited range in angular terms over which you really want to be sensitive to an obstacle. You don't want to be influenced by an obstacle that's behind you, for instance. And so the range is controlled by certain parameters in these functions. We'll typically just put a Gaussian on top of a linear function. We take a linear function, multiply it with a Gaussian, that gives you this red curve, and the width of that Gaussian will control the range. Technically speaking, the range goes all the way here to 0, and corresponding on the other side, because even when these values are small, you're still being attracted, right? But there's a measure, there will be, so there's a weak contribution here that could be overruled by other contributions while it's strong here in the vicinity. So that's sort of the mathematical thing. So I'm not writing down the equations here. You will have a chance to read papers where we use different equations. In fact, this is really the spirit of qualitative dynamics. The important thing is this attractor layout. And I'll show you about bifurcations in a moment. And then you can use different equations to realize it. Historically, we used actually somewhat complicated equations that were very nicely tunable with parameters. And then later, actually, we started to simplify, just use Gaussians and linear functions. And so there are different concrete quantitative ways to create these qualitative dynamics. So that's the terms. There's an analogous term for obstacle avoidance. You have the same thing, the zero crossing, the slope, and the range. Now, when you combine multiple contributions, you'll have to decide how these multiple contributions interact, or how do they act together? What happens there? And so I'll do this with this example of two target contributions, even though it's a bit academic. We don't really do it this way in practice. We actually usually have some sensory system that decides which target we want to go to. But just for illustration, because it makes it easier, and then we'll go to the real case, which will be obstacle avoidance. So let's say if I have two targets, and these two targets are close to each other in angle, so that I could be heading into that general direction. And if I were there, my vehicle would be on top of or close to either target. And so in that case, I would say I want to fuse the information from these two targets. So if these are the individual targets, for instance, with the attractors, two forces, I just add these forces, then you get this red curve, and that would have an attractor in some arithmetic mean, depends on the slopes, arithmetic mean between these two targets, and the slope is a little bit steeper. In fact, it should be twice as steep. If they were really very close, overlapping, they would be twice as steep. And here it's a little less than twice, because these are not exactly overlapping. So that will be an averaging behavior of these two contributions, and that might be reasonable for targets that are very close. These could be even just different sensory estimates of the same target. When these targets are more in conflict with each other, so for instance, that when you're heading to target 1, you're not reaching target 2, and vice versa, then you might want to have a case where the system decides between either targets. So for instance, one contribution could have this as an attractor, the other contribution here would have that as an attractor, and in the superposition of these two forces would be arranged to be such that it has an attractor on this side and has an attractor on that side, and there's actually a repeller in the middle. And that would mean if you're already heading in a direction closer to this attractor, you're going to end up in this target and corresponding on the other side. So you make a decision, and the decision would only depend in this case on which target you are closer to initially, when you're initially heading in this direction. So that's what we call a bistable dynamical system. It has two attractors and two basins of attraction. So as a basin of attraction is here an interval, or generally a connected set of initial values from which you will converge to the attractor. So here the repeller divides the heading direction into two parts, one where you're attracted here and one where you're attracted there. Remember, the heading direction is always periodic, so there is actually another decision point, or let's put it this way: when you're going away from this no, this is actually attractive. Okay, we'll come to that. And there's another repeller in the back of the system. So where the two in the opposite direction of these targets, there's also another repeller. So the change between these two situations is a bifurcation. And you see that immediately because the flow is qualitatively different, right? Here you have a single attractor for the entire interval. And here you have two attractors with a repeller. So these two flows are not qualitatively equivalent. And that means there's bifurcation. And the bifurcation is a pitchfork bifurcation. You have the one attractor colliding with another attractor at the same time as the repeller in the middle collides. They fuse and only one attractor remains. And this end here would be for large distances between the angular distances between the targets. This would be for small ones. So again, this is large distance, right? Two attractors, one repeller, and then small distance, that would be small distance, right? There's only one attractor left. These hypothetically the two individual attractors have fused. So somewhere in between there will be a instability where essentially this repeller becomes very flat. Imagine you push this in, at some point will be just very flat, and then next moment in time there's a single attractor left here in the middle. Next moment in distance between the two targets, there will be a single attractor left in the middle. This pitchfork bifurcation comes about in this case because this is a symmetrical case. I just constructed it to be symmetrical. That is, these two individual forcelets, this one here and the one here on the left, are the same. And therefore, the only way under which you would make a switch is if the two annihilate. You could have generally a asymmetry, that is, one target is much more attractive, maybe something about some sensory quality, or you have some information about which is the more likely target, then you could make that forcelet much stronger, much steeper slope than the other forcelet. And in that case, actually, there would be a loss of symmetry that would change this bifurcation diagram. What would happen is that one of those attractors is weaker and then actually collides with the repeller separately in what is a tangent bifurcation. You can think of this branch here lifting off this pitchfork, and the other attractor actually just continuously changes. Then you have one attractor that disappears and the other attractor just goes through. We'll see an example of that in a little while. So this is a bit academic example, because usually we do the targets in a perceptual or representational stage of the motion planning, not in the actual motor planning. Now, what we actually do is use this to make decisions about obstacles. This is for good reason, because we usually don't really have a perceptual representation of obstacles where we decide to fuse or not fuse different sources of information about obstacles. Because what's an obstacle? Just anything that is not the target, but that is in the way of the robot. And you don't really care if different measurements that you make on an object are different obstacles. You just want to avoid to be at that location where you get that measurement. So here, let's look at first the case where there are no conflicts. So I'm having an obstacle here and another obstacle there. Here is the target, and in matching colors, you have the contributions to the dynamic. So there will be an obstacle contribution that has this here as a repeller. There's an obstacle contribution that as an repeller. That will be these two directions to the two obstacles. And then the target would be this pink contribution that has a attractor negative slope here in the middle of the whole thing. Here, the black line is the superposition of all of those, and this is arranged to be such that the superposition, the black line, actually preserves all these individual solutions. So you see there's an attractor in the middle, and there are repellers here exactly where the individual contributions say there should be a repeller. So that just fits very well. And that's arranged by choosing the parameters of these widths and strengths and locations of the different curves to be right. So for this to be the case. You see that there are two additional attractors that we didn't usually previously think about. One is here very far out and one is here. So one corresponds to going around the obstacle this way or going around the entire set of obstacles that way. And they sort of emerge from, well, from the fact that the individual forcelets here, just take maybe this forcelet as an example, they have some kind of like a semi-attractor in a sense on their outer limit. You know, if you just look at this orange curve here, then you would say, you know, this is like a negative slope. It just doesn't go up, it doesn't go through it, the negative slope, and then it becomes tangent, ultimately it wraps around. So that's like a half attractor that is, it's attracting from the side. It's actually the repulsion from the obstacle that is attracting toward the boundary of the obstacle. But it doesn't really stabilize against moving further away from that. And similarly, you could say where this force that sort of disappears, it's like a semi-attractor that is, when you're a little bit to the left, you're pushed toward this zero crossing from the, ultimately from the obstacle that's in there. And so when you add all these different forcelets, there are contributions here from the target that make the semi-attractor into a real attractor. Semi-attractor is not a formal term. I'm just making it intuitive, right? It's a boundary of it's a zero crossing that that is actually, technically speaking, a marginally stable state. But it becomes a real stable state because of this attractive forcelet from the target. So the semi-attractive, which becomes a real attractor, and same here. So this is a more complex landscape where there are 3 attractors and 2 repellers. So if we now move the 2 obstacles toward each other, so that now passing is not correct, it's not consistent with the constraints, then we would arrange, again, by choice of parameters, for the forces to go through bifurcation where the 2 attractors in the middle fuse and leave only a single repeller. So it's the 2 repellers in the middle that fuse to leave only a single repeller in the middle. And the system actually happens to have these other attractors on the outside, which they persist, which were not really, you know, in individual contributions. So that's truly emergent from the arrangement of all these different forces. So that's another pitchfork bifurcation. If you look at it, it's a pitchfork. It's the subcritical form of the pitchfork bifurcation. Here, the parameter is the increasing distance between the obstacles. At large distance, you have the 2 repellers with an attractor in the middle. At small distance, you have the single repeller left. So it's the repellers that collide, and at the same time as they collide with the attractor and turn into repeller. So compared to the pitchfork we just had, this essentially attractor and repeller switched. Here the attractors on the outside and on the handle of the pitchfork, and the repellers inside, and here the repellers on the outside and the attractors on the inside. One is called the super and the other the subcritical pitchfork bifurcation. Mathematically, if you have a model of these, you can just say, if I let time run backwards, then one picture turns into another, right? If I take the dynamics, let time run backwards, then an attractor becomes a repeller and a repeller becomes an attractor. And that's how you can think of it. It's actually a symmetry operation. If you let time run backwards, then your phi dot, the dot changes sign. So everything is flipped. You have changed the right-hand side of the equation, and then you get the opposite bifurcation. So that's the local bifurcation. Again, there are these other attractors on the outside which are not really affected, and so the system would be staying in either of those, or switch to either of those once it goes to this bifurcation. So this, again, the symmetrical case. The symmetrical case really based on assuming that the repulsion from these obstacles is exactly the same. These 2 orange curves are exactly the same. And in general, this might, again, not be the case, might be the more typical thing. In fact, the 2 obstacles here are not drawn to be the same, but this is just a made up illustration. We'll see next week when we really think about the sensory sources that specify obstacles. We'll see that this is sort of the critical limit case. If you have a ultimately, when you collide, there will be typically just one point on which you will collide, one point on the robot and one point on the obstacle. And so there is one most important contribution. And the only case where that's not the case is if there's an exact symmetry, so that you would be touching two obstacles at the exact same time. And this is of that case. So if we fix that case, then we have as a side effect also that we have covered all other cases. And again, the other case would be the breaking of the symmetry. If you break the symmetry, then one of those repellers will collide first with the attractor, and the other one will then be unaffected and just goes through. This will be the pitchfork turns into a tangent bifurcation plus one additional repeller or attractor if you break the symmetry that underlies it. Oh, yeah. Good. So you see that these bifurcations are useful because we can sort of organize the whole range of solutions. If we do this, we can say that any initial heading, we know what's supposed to happen under which condition, and so they organize the behavioral system. But that's of course only true if the solutions that will be observed are influenced by the attractors, so are close enough by the to the attractors, then so that we can actually say that the constraints imposed by the attractors actually apply. There are some papers in the literature where people analyzed the dynamics, but found that the timescales were such that the system wasn't tracking the attractors, and then that was somewhat pointless. So that is actually really the trick, and I will contrast this a little later with a potential field approach, like 3 lectures down, where that's not the case. In the potential field approach, you also have attractors and so on, but the behavior consists of going to the attractor. And when you are in the attractor, you're no longer moving, you're just sitting there. Here, you are always in the attractor at all times. And so we will have to think about how that's possible. But that makes it actually really easy. That is, we only have to design the attractor solutions, not the whole ensemble of solutions. So we only pay attention to this bifurcation here, and then the dynamics of the flow. So the solutions for all other initial conditions are just derived from that. That's a really elegant thing. That's how we can use bifurcation theory to design the dynamics. So the only thing that you might wonder about is how is it possible to have interesting looking behavior, complex, flexible behavior, while you're sitting in an attractor, right? That would be a bit counterintuitive, because attractors are constant solutions. So wouldn't you be just sitting there and doing something really boring? Yes, that's true. You would, in fact, as we initially said, if you have just this, just moving to a target, then after some initial transient, your heading would approach this heading. So then you would do something boring and just go straight to the target. So the fact that you're showing maybe complex behavior comes from the fact that the environment is maybe more complex, and that there is some way of how you keep track of how these environmental constraints, the behavior constraints that come from the environment emerge as you move, right? You have sensory information or some kind of world model about where the obstacles and targets are and where you are relative to them, and therefore the behavioral constraints change. The heading directions that are to be avoided or to be achieved vary in time, and therefore the attractors and repellers move, and then you're moving with the attractors and repellers, and that is actually what makes it complex. And here I'm illustrating this in this example, and this is maybe the opportunity for you to tell you about a trick. So this is a little bit trick, this example, because a general problem that you will encounter when you read this literature. So it's a kind of a trivial problem, but I need to make you aware of it. So in all of these papers that we wrote and all our colleagues wrote, we use the mathematically correct sense of angles. And so for some historical reason in mathematics, when you go counterclockwise, you call that a positive angle. So the way the clock goes is actually it reduces the angle that the what is it called, the Zeiger, the clock's arm, or forgot the name for that, forms, with some arbitrary axis, because it goes to the right, and that is a negative angle, so decreases, and it's to the left that the angle increases. And that fact makes that when the vehicle moves to the left here, moves to the, turns to the left, the angle would increase, and that means here on these plots you move to the right. And so in all the publication, that is the case, and that requires some mental flexibility, because you have to say, oh, it's to the left of this, and therefore on this graph, it's to the right of that. And so in my lectures, I've actually arranged all the figures to be flipped. So these figures pretend that this angle was measured going to the right. But in the mathematical implementation on the robots, in the papers, it's always really mathematically correct. So the angles are actually defined to the left. So I've been cheating by flipping some of these plots around for the lecture's purposes. So I will always pretend that things that are on the left in space are also on the left here in these plots. So you need to know that before you now understand what's happening here. So here, for instance, is a configuration. This is actually from a real robot run, except for this flipping of the plots. So the robot here is in initial position. There is an obstacle here. The target is further away and is sort of, in terms of angle, it's on the right of the obstacle. And the vehicle is initially heading a little bit to the left of this obstacle. So here, the obstacle contribution here makes this repeller, and the target makes here a attractor that's a little bit to the right in angle. Now, again, with that trick of the obstacle. Here's another sort of semi repeller. No, it's actually a real repeller here on the back, sort of in the opposite direction. It doesn't really matter. And there's another attractor here to the right, and that attractor essentially corresponds to the vehicle going this way around the obstacle to the target. But the initial condition of the system is close to this attractor, so it's really sitting here in this attractor, and that's why it will be steering around the obstacle this way. You see, this attractor is actually a little bit to the left of that direction, so the heading is actually being repelled a little bit from that. And in the next moment in time, so a couple of steps later, the vehicle's position was like that. So it's now, heading further to the left, so to the left on these plots. And in this position, it has also moved forward. Under this position, the bearing of the target is actually now closer to the current vehicle's heading than the bearing of the obstacle. See here, this attractor moves through the bearing of the obstacle, so it's flipped around. Sorry, the green curve, by the way, is the sum of all these curves. And here also the green curve is the sum of these curves. And so you're in this attractor here now, and now that's closer to this than to that. The other attractor has actually just disappeared. There's a tangent bifurcation, as you see, for this solution. That's essentially saying that at this moment, the other path going around the obstacle through the bottom here is no longer viable and it's become unstable. So the reason I'm showing this is to show you that the vehicle does something other than move straight and some complex path, really because these different contributions shift around in time. They shift around here, the target shifts around in angle. Sometimes they might also shift in terms of slope because the obstacle contributions actually depend on distance and become larger, more forceful when you're closer to the obstacle, as you might be here. And what the attractor does is that the solution of the dynamical system that will be handed down to the motors is tracks the attractor. So it is not exactly sitting in the attractor because there will always be some delay depending on the time scale of the dynamics, but you will be always following the attractor, so be close within a certain limit of precision, close enough to the attractor. So in other words, you get this flexible behavior, and therefore you're sensitive to the bifurcations because you're tracking the attractors, and the attractors move. So we did back then a real vehicle implementation is ancient work. This was the state-of-the-art robotic platforms, like about 1 meter by 1 meter, and we used a very fancy way of the cameras here. We used some visual thing that was able to detect these obstacles because they stick out from the surface. So by doing some stereo method, everything that we, certain kind of approach where you're very low level approach where you get some information about anything that's not in the surface. And therefore it was, for instance, here able to detect this obstacle and then move around the obstacle. And there's some other obstacles. And the target was actually here only by that reckoning. That is, this vehicle had good shaft encoders and was able to predict where it is. And so it has a map where it is. That's the other problem of navigation. You know where you is and where you're going. I'll come back to that. So here was solved trivially that the system had some Cartesian map and was calibrated by initial condition. This was, of course, a map that got worse and worse in calibration as you moved through the plane, and therefore it reached the target. So there's an example from work like that where the actual measurements are not objects. You don't actually have a way of how to really, detect the objects, but you only want to know places in the world where you don't want to go. So this approach had a couple of points, like all these points here were points it wanted to avoid. And then using the approach I'm hinting at, it actually made this very smooth kind of movement. I will return to this point next week because there is an issue when you do that of how to integrate all these different contributions, because if you consider each of these measurements an obstacle, then you have actually some problems, because there would be a lot of votes for those obstacles that you have a lot of measurements on. But maybe there's an obstacle like this one that has a few votes, but you still want to avoid it. And that's connected to a problem. And I'll discuss that next week. We've sometimes called that in our papers that this was a symbolic approach. It's not maybe quite the right term, but meant that we really talk about different objects like obstacles and targets, and each makes a contribution to the dynamics. One force that comes from one object like that, and that would be possible under some circumstances. It's likely that humans and animals actually look at the world that way, but it makes really demands on the perceptual system. You would have to have some way of detecting an object and distinguishing it from a different object. And if you do that, then you might actually really be influenced by two objects forming an obstacle more than by a single object forming an obstacle. But for robotic navigation, that might not really be necessary or even useful. And next week, I'll talk about a subsymbolic approach in which you take raw sensor readings without any perceptual processing that breaks it into separate obstacles or separate objects and determines parameters like their center of gravity and their width, for maybe some average distance, to then insert them into the equation. And that actually is the approach that really works very well in practice. So I'll come back to that next week. It will be a recurrent theme in the course. Now I want to spend the rest of today's lecture to show you that this kind of description actually does capture human navigation behavior, human locomotion with respect to how you displace yourself in the plane. Historically, I have to say that it's kind of an interesting story in that I came to this sort of robotics work from doing models of behavior, of motor behavior in various forms, and some of that will show up in the second part of the course. It was really about limb movement and timing and things like that. And when I was confronted with the robotics problems, I really had the job to do a robotics contribution when I was first a group leader here at the INE many years ago, like 30 years ago. So I just invented that we're using the attractors, and so this was the philosophy I had. I didn't really know if this was biologically plausible in the concrete terms. It was a more metaphorical use of these ideas. And then I was invited to Brown University, where Bill Warren, a psychologist who's been close to the earlier work I did. So I gave some lecture courses, and we talked a lot. And he ended up doing a project with, it's published here under the name of the doctors who did that vision, that kind of did experiments on humans that measure something like that. And you will see that it actually really matches what we had postulated. And they did this in virtual reality. I was in that cave. It was actually very impressive. Just, I mean, this is long ago, right? This is when these caves were not yet so common. So that a huge virtual reality cave, you know, you have to have a huge room so you don't run into obstacles in the real world. And then they were able to play something in this head-mounted display. You could see stuff in the world. It was really impressive. Like they had a carousel, and when you stepped onto the carousel, you really had some sense that you were moving, even though you were, of course, not moving at all. That's really nice. And they used this because then they could really control the metrics of layout between target and obstacles. So they looked at human locomotion. What they did is, as a participant, you put somewhere, you began to walk, and after you walked, I think 1 meter, then in your display, a goal appears, and in what I'll show you in a moment, also maybe obstacles appear at different angles. For instance, these different angles from the straight heading, and also at different distances from the participant, right? So this is a way how to get you into different configurations that maybe if you were to see the scene from the very start, you wouldn't even get there. And so and the task was to walk to the goal. These goals and obstacles were actually sort of cylinders in this visual display, and they had different colors, and you know, one color was obstacle and the other color was target. So in this first set of data points, it's all targets. And so what they looked at is phi dot versus phi, right? Inspired by our approach to find the attractor dynamics here. So this is plotted a little bit differently because the goal position, so it's centered on the goal angle to the goal. So this is phi minus psi. So rather than having different locations where a goal is, they put that on top of each other by subtracting the goal heading from the current heading. And so it's all, the attractor is over to 0. See the phi dot, see it's like this negative slope going through 0, right? So as they were coming close to heading right to the target, the heading, the rotation rate went to 0 very nicely. And so ideally it would be just this one curve, right? And that will be really the forcelet, literally, that we're looking at. Of course, what really happened is that when you're walking after this 1 meter, the obstacle comes in at these different angles. So here it looks like it's different values, but of course it's the same heading, but the function, in a sense, the force that is just turned on at different moments in time. And so there is some transient where you, in a sense, have to get onto the curve, right? And that's not consistent. That is, at this value of heading, you have different turning rates depending on when this was turned on. And this sort of reflects there is a hidden degree of freedom. That is how you could say that what happens is that the dynamical system, if there's that kind of dynamic system that we're postulating, it's suddenly being turned on, and you have a transient from behaving as the previous dynamical system, which was just flat, no information, to the new dynamic system, until that actually influences you, and you'll see how they corrected that equation to get that behavior right. Similar for the distance. So when you have an obstacle at one particular heading, this was like 20 degrees, and it comes up initially at different distances. Then you see when it comes at a closer distance, you get a stronger maximum turning rate, so it makes you turn more sharply than if it comes in at a larger distance. But they are overall still, and again, these different, these might actually really be different, right? Because it's really different configurations. So the dynamic system doesn't have to be the same for these different values. And they similarly measured the obstacle contribution. So the obstacle contribution was always in the presence of a goal, which was visible at some depth. It was always behind the obstacles. And after walking toward the obstacle, toward the target, obstacle appears at different angles from your current heading, and again at different distances from your current position. And then looked at these contributions, and you see here, this is the 4 meter condition for different angles, and this is the 3-degree condition with different distances of the obstacle. And again, you're seeing heading now centered in the obstacle. So here is the obstacle. And so you see this is like the positive, so in a sense, there's a zero crossing here imagined, right? And the slope is positive. That will be the repulsion force. And it's strongest when the obstacle is very close to where you currently are in terms of heading, right? Then you would be repelled very strongly and less strongly when you're here. Again, ideally, these curves should lie on top of each other, or I mean, at least be aligned. And that would not be the case in that you have some transient to actually get onto that. And you see, they actually convert you to a attractor, right? This is actually an attractor in a sense. It's, again, complicated by the fact that under different conditions, you shift this by a different amount, which would be that attractor on the outside, because you also have a target to go to. And so this is where the obstacle repulsion and the target work together to build up an attractor. And, you know, again, it depends on the distance in the sense that when the obstacle appears very close, you have a large turning rate. And if it's further away, you have a small turning rate. So qualitatively, it really matches this quite well. They actually really compared that to the prediction quantitatively. It's the same notation as we have, just the G for goal and O for obstacle. Use the same variables. And so they fitted the dynamical system. And of course, the dynamical system that I was just talking about isn't exactly right, because again, these curves should be the same at the same heading. You should have the same curve. And that's not the case. And the correction is essentially, they did it by having a second order system. So like a damping term that amounts essentially to some inertia, that it takes some time to get to the attractor. And I will make it part of the exercise to analyze that a little bit yourself. There's actually, I would say it would be also possible to model this whole set of data by using the first order dynamics that we had used, and just keeping track of the fact that there is that transient that you switch on the term at a certain amount of, at a certain moment, and then yeah, there is some kind of time needed to get onto that dynamics, and that is something like inertia. It's maybe not a physical inertia. So when you have a second order term, you see here, this is essentially the attractor dynamics in linear coordinates, which is a good approximation when you're close enough. So, you know, think of this as, you know, ignore the moment that it's second order, and just think this would be like phi dot, and then you would have phi minus psi with a minus sign. So it would be a function that goes through 0 at phi psi. So this function here, and has a negative slope. And this says that that slope is distance dependent. There's a constant term, but it's also a distance dependent term that is when you are far, when the target is far, then you're turning less sharply. This term is weakened when the target is far. When the target is close, it's strong, in other words. And then this is a obstacle avoidance or repulsion term. So it has phi minus psi, the same form with a positive slope, right? That is repulsive. Yeah, this here. And then they also have a range term. They used the absolute value. We've typically used the Gaussian. That's really just a question of quantitative form. So this says that that term will fall off when you're far enough from the obstacle. That makes this force-let character, right? That it falls off here. And there's a distance-dependent term again. So if the distance to the obstacle is large, then there is little influence of that obstacle. And remember, they vary the distance from the obstacle in the experiment. So this is one of these distance terms for the obstacle, and that's the distance term for the target. And the target term doesn't go to 0. So if the distance to the target is very large, you still have some attraction to the target. So it's really just this enhanced attraction to the target when we're very close. While the obstacle, if the obstacle is very far, then you are no longer influenced by the obstacle. And so you extended, yeah?
I have a question.
Yes.
So we see that you modeled the function with an exponential function for the regarding the distance to the target. In this case, I guess you chose coordinate, Cartesian coordinates. If we choose polar coordinates, which is also possible.
Yes.
Would a sinus function be useful as well?
So this is actually polar coordinates in the sense that these distances, they are, so you're not representing xy of the target and goal, but you're measuring the angle to the goal and the distance from the goal. And similar for the obstacle, right? It's a polar coordinate system that is centered in the observer.
Okay.
And so this exponential, the distance dependent to, it actually empirically, it fits well when you do it exponentially. We've also done that in our vehicles. I didn't show you the equations we use for the vehicles. So exponential form has this advantage that it has a clear scale, right? It's exponential fall off. You can really say that the same percent change in distance will have the same factor change in the strength. So it's a good way to characterize that. So that's very natural. What they didn't do is they didn't take into account that these are angular variables, right? So in our robot models, we put a sinus in function of these terms, and we actually write this as a cosine of that thing. And we have to lift the cosine to be only positive. Similarly, we'll put a sinus on this term. And that's because it's periodic. So in the robot, that's really important because the robot goes in all kinds of directions. So also sometimes might go in the opposite direction of one of those contributions. In their modeling, the experimental paths they had for the human were quite restricted in how much they turned. And within the little turning that they got, there wasn't really a big difference between the sinus and the cosine term. That's why they got away with that linear function, which is easier to handle mathematically.
Okay, so if there's a possibility for turning multiple times, you need the sinus or sinus in this
For instance,
case.
if you just were to do this on the robot, then if the robot is, and you introduce a real conflict, like the obstacle really forces you to move against in the opposite direction of the target for a while, then this would be quite wrong. You would get an instability, that if your target crosses in the opposite direction of the target, then there would be a jump from a very negative to a very positive value. It would be really awful. And so on a robot, this is not a good solution, but around just a small set of heading directions, like in these examples, they were just looking at a limited range, then it didn't really matter. This is more a fitting model. It's not so ideal for the robotic case. Is that clear?
Yes, it became clear.
Okay, thanks. Good. So the second order system is really just a sort of a little correction of the first order. And to understand that mathematically, I thought it was a nice little exercise for you guys to sort of see if you understand this well. And I put on the exercise sheet, I'm inviting you to think through that in two ways. So one way is to just see, could you get this here from the equation you're familiar with? That I didn't write down the equation, but the equations of the vehicle case, and on the exercise sheet, you have a chance to examine that first. And that is when you're essentially saying that there is no inertia. So making no inertia will mean that the inertial matrix that you have here in front, there's a factor here in front, hypothetically, that's the inertial moment. You make that 0. So you set that equal to 0. See, then you put this to the other side, and then you essentially get the equation you're familiar with. And the other possibility is to really take this whole dynamical system as it is here and analyze it for its fixed points. This is a second order dynamical system. So you have one more variable. You have to introduce, essentially call the phi dot, give that some name. I'll invite you to sort of name, then this is the derivative of that variable. And you have two equations. And then you can analyze the fixed points and see if this has the right attractor repeller layout in this two-dimensional space, and you will find that it does. So it's really like a lifting of the first order approach to include essentially a low-pass filter. you could say. The inertia term does something like low pass filtering of the solutions. So it's a little, when there's a force, it takes a little while to actually go in the direction of the force that the first order equation has. So with this, they were able to fit the data. They have a few fitting parameters, so it's not rocket science. You see, there's this parameter. So 1, 2, 3, 4, 5, 6, 7 parameters, right? So yeah, well, they have quite a bunch of conditions. At least it shows it's possible. Even the details seem to match quite well, and it's quite impressive. So it's possible to do that, right? So this model really captures. Yeah, and here's these are the different conditions I showed. So it's quite a set of conditions. They also then demonstrate something was really fancy. So they just showed, what these are example solutions from the obstacle. And this is a case that wasn't actually exposed. I don't think this is what actually happened, just an illustration what happened. So here's an interesting case. And this is one where they actually have experimental data. I think it's, this is what they actually had in one of their settings, where they had a configuration. So this is an obstacle. And these, I think, are under two different conditions where there are targets here, and they vary the angular configuration of the obstacle relative to these targets. You see, it's a little in, little out. And so this was set up to be just around a decision point. So you imagine you're heading here, and as you start to run, you have to decide if you go around the left or go around the right. And that might also depend on whether the target is close or far, and on the angle here. This is the goal offset angle, and then these are the distances where the target is. So if the target is very close, you might be more prone, I think, maybe to go, I think then you're more prone to actually go this way, yeah, and so on. And so this was something that was done with both on the model and the data. So it is supposed to not be fitted, but just be emergent. And it did turn out that the humans have a predictive characteristic, so they do both of those. So it's not quantitative in the sense, it's not saying how many % time you choose that route, because in the model, this would be a complicated thing with some stochastic decision making. So it just shows that in the model there are slight differences in initial condition, where sometimes it takes you to one solution, and if you're a little bit to the left of that, it takes you to the other solution. And empirically, you find that people actually make these decisions, so we really make these different solutions. Sometimes they go around this way, sometimes they go around that way. It's not explained by the initial position. It's essentially some perceptual decision making people make. And so you see there's a systematic dependence that is related to the degree of stability of the different solutions, where they go around, I think around the right here for small angles and all the distances, and then they go around the left for these larger angles and I guess a larger set of distances, right? So it's even subtleties were explained well. Yeah, so I really find that quite charming, given that the model was really not developed for this. Now the only thing they changed is this low pass filtering, but everything else is this robotic model. Really quite amazing. So the attractor dynamics model, even though it was freely invented, does actually account for human locomotory behavior in this kind of setting. This is the first study, interestingly, that really described the kinematics of human movement this way. There had been a lot of work, and it continues to be a lot of work, and how humans know where they are when you ask people to estimate where something is based on a map, or for instance, you have people see a scene, and then they have to close their eyes and make a few steps, and you can read off from these steps how well they know where their target is. So that's what navigation is. Ambivalent navigation both means achieving particular movements and knowing where you are, and these are very connected, right? In sailing, navigation is, again, both of those. That is the task to know where you are, and also how to get somewhere. And knowing where you are is important for getting somewhere specific. And so there's been much more work on knowing where you are than on actually showing how you move. And part of that is kind of difficult to see. You need this very good control of virtual reality to even be able to parametrically vary conditions. So you can really say at which time do you start to be influenced by what kind of constraint, and parametric, scan that out. So this is really a good theory for that. Now I want to show you 2 lectures down. I'll show you also this navigational part and show how these two are connected. And then it turns out that many of you might have heard about that there are maps of space, sometimes called cognitive maps, that are linked to hippocampus. Someone got the Nobel Prize for that a few years ago. And so that's a hot topic. I mean, actually, it's already well studied, but it's certainly still a lot of activity in that field. And people are beginning to use these cognitive maps as metaphors, also even for general thinking of where you say you have some spaces in which you move when you think. And we are influenced by ideas like that. And the point, so I'll show you a little bit how that's connected. But one thing I want to point out right now is that the substrate on which all of this is built is heading direction. That is, all this, the way you use maps and then you measure maps is about looking from how animals orient toward locations that they want to achieve or they want to forage. So for instance, the Morris water maze is a way to assess where animals think they are. It's rats swimming in water, which they don't like, and you've trained them to swim in particular directions where they know in that little stadium there is actually a platform to stand on just below the water, but so that they will be safe from the water. And so by looking at in which direction they're initially swimming, you can estimate something about their cognitive map, where they think the platform is, depending on the visual horizon, for instance, they have. And there are cells in hippocampus and entorhinal cortex that seem to be coding for, in sense of tuned to heading direction. So this heading direction is not just this arbitrary variable. It's actually really something that reflects behavioral, something that structures the way we orient in space. So somewhat deep in that way. Good. With this, I want to close today's lecture.